This is the last week of class.
Yes.
And what I'm planning to do is the makeup quiz will be Friday for everybody. It'll be a catch-all. If you missed a quiz, then that will replace the missed quizzes regardless. There are some special problems that I have to deal with. But and the other thing is, what I'd like to do today, I want to sort of almost wrap up everything. We're going to do S parameters, we're going to do 2-port, 3-port, 4-port. I'll go through the Wilkinson divider, and I'll talk briefly about filters, but everybody in here should have had filters. You should have had high pass, low pass, band pass, and band stop, correct? Is that right? All right. Did you have a question?
Yeah. Are we going to get quiz grades back? Do you have those done?
I will get them back to you. I've got 2 sets of things. I've got to get that 8-bit stuff back. It's right now with somebody else, and then I'll get your quizzes back, all right? I'll bring them.
I'm sorry, I didn't mean to interrupt. I was just, will we know, so for the makeup quiz, that we're going to do Friday, is that will we have a grade before then so we can know what we...
You should have all your quizzes back. I handed them all back. I mean, if you're looking for specific grades, you can see me. I'll show you your grades if you want them. I mean, that goes to anybody. If you want to see where your grades are and how you stand, then I'll give you all those. And as a matter of fact, I'll email them to you if you'd like. I have to only mail yours to you. All right? I almost hate to say that because I know it's going to happen. But I'll be willing to do that. One last,
The makeup quiz,
Friday.
Do we take it even if we haven't missed a quiz, or is it just when we miss quizzes?
You might as well. Here's why. It can't hurt you. I'll replace your lowest quiz grade.
Okay.
Yo.
What
So-
now? Huh?
I guess I'm gonna keep the conversation going. What's the makeup quiz gonna be on?
Paper.
Every.
It's not all inclusive. It's going to cover the last topics that we covered. S parameters and filters.
So that's like the equivalent of dropping our lowest grade, we're replacing it.
Kind of, sort of. We can play this game all you want.
It's only
Ultimately, it comes down to this. All right, your best quiz grades will be used. Does that make sense? All right. I'm not trying to hurt anybody. All right. There's people that have had sicknesses. They've had all sorts of things. We've had accidents in here. God knows what else has happened to people. So I'm trying to be good. And we didn't get a phenomenal number of absences due to COVID. Thank God. The first semester we had COVID here. I had people that literally missed a third of the class.
Yep.
All right, so I don't think we have anybody in that case here.
They're probably not here if they were.
Well, I mean, there are probably people that dropped
Yeah.
but I don't know. There's been some crazy stuff this semester, and so I'm not in this class, but in another class I have. I've had people burned. I've had people robbed and beaten. I've had everything you can imagine. I'm not kidding about this either. I've never had that in my life in a class that I knew of. By the way, Jacob, for what it's worth, you guys played your hearts. I don't know what to say. That student section. I'm glad I didn't get the rap for that one. That's the one thing. All right. So let's go. And are there any other questions? All right. Now, do y'all remember? I know we had a break. We did S parameters, right? I'm going to review these, and I want to just go through a brief S parameter 2-port problem before we go into 3-port and 4-port. That would be the last major topic. You've had filters, so anything I deal with filtering, I assume you've already had. I'm not going to go through. Have you all had Butterworth filters and Chevy-Chef filters? You have? In what class, by the way, Beth?
Communication systems.
How many have had common here?
I'm in it now.
All right, if you've been exposed to that, that's the key thing. Dr. Whitmer's book on this stuff is not something where it's all-inclusive in how to design exact Chevy-Chef and stuff. Most of this is done with computer programs anyway. All right, so now back to this, S parameters. I gave you some problems on this. I don't know if you did them or not. Y'all recall that? There were basic problems. How many do? I'm asking a lot right now. All right. Well, we need to review it. So anyway, in general, S parameters for 2-port, like this. This would be port 1. This is port 2. We're going to have an incoming signal V1 that would be plus, and an outgoing signal V1 minus. You're going to have an incoming signal V2 plus and an outgoing signal V2 minus. This is the standard way they designate it. In general, these are transmission lines or waveguides. The symbol for the S parameters generally is S. It's a bold S with a bar over it, or in some cases a double bar to indicate a matrix. That's the first step. That's what it looks like if you see most block diagrams. It'll be something of that, to that effect. Then there's the equation that governs input-output relationship. So V1 minus, V2 minus, that's usually a block, is written as S11 times V1 plus, and it's going to be plus S12 V2 plus, then this is S21 V1 plus, plus S22 V2 plus, and this is commonly written like this, where they have S11, S21, S12, S22 times the block of V1, V2 plus. That's just the common way it's designated, and that's what it stands for in relation to this drawing. The way this is usually done to obtain S parameters, they use something called a network analyzer, and they'll drive the input port, they'll have the ports matched to 50 ohms if it's a 50 ohm transmission line system. And what they'll do is they'll get the S parameters versus frequency, both magnitude and phase. That's very, very important for amplifier design, especially when you're doing high frequency amplifiers in the microwave band for radar. This is not low frequency audio amplifiers I'm talking about. It's high frequency stuff, power amplifiers. So when they do this, first thing they have to do is review and make sure you all know how to do it. Y'all remember this class now? I'm going to put up the most simple one I can think of, and let's go through this to make sure everybody understands it. So, for that, we're going to have a transmission line. It could be a waveguide, by the way. Doesn't have to be a transmission line. And here, well, actually, what I'll do is this. I'm not even going to draw the box here. I'll show you how it would appear to you. You'll have this, and I'm just going to put a resistor, make this Z0 and make this resistor just R. I want to do this more generally than I usually do. Here's port 1, port 2, and again, V1 plus, V1 minus, V2 plus, V2 minus. So now, I want to go ahead and get the S parameters. Now the first one, S11, is the most direct. Now I put this in terms of just an R and just Z0, so you can see that how you can adapt this to almost anything. I'll go a step further. If I were to put impedances here, we could write a general equation for any pi filter type of application. Do y'all know what pi filters are, class? There's usually T filters and pi filters. A pi filter looks like this. It looks like the letter pi. And this would be a pi filter right here. Gets its name because it looks like a pi. Then a T filter would look like this. And this would be a T filter. Now you can see that either one of these could be used in place of that resistor. Y'all see this, class? These are things. In general, what they'll do is they'll put impedances Z1, or they'll call this Z1, Z2, Z3, then Z1, Z2, Z3. And there's an actual equivalence between these two. You can create a T filter that has the same response as a pi filter and vice versa. Just so you know this. Did y'all see pi filters? What's the most common application of pi filter, just for everybody's benefit? I want you to think of one thing that is done all the time when you take AC to go to DC. Full wave rectification, right? Whenever we get full wave rectification, we have a problem with ripple. Y'all remember that? How many remember that? Right? If you had into this pi filter, you had a waveform that was doing this. Then what they do is put a diode stop here, so it can only be current going that way. And what they do is put a big old cap right here. I mean, when I say big, I mean millifarad kind of cap, something enormous. Then they put an inductor in series here, and that inductor would have an impedance at 60 hertz that would be significant. Y'all hear me? But at DC, an inductor looks like a short, right? Y'all remember this? Then they put another whopping big capacitor over here. And outside here, if this is what came in, what would come out would look like this, with very little ripple. There would be a voltage. This would be VDC right here, and that VDC right here would be the peak level right there. Now, that's how they actually take a standard full wave. You know, when you take transformers, you take like 110 down to 12 volts or 110 up to 2,000 volts or whatever, right? And then you have to rectify it if you want DC. So they do it with a diode. This is actually half-wave rectification. Full wave would have 4 diodes. This is half-wave. But it would still effectively give you a DC out. How many have seen this before I keep talking? Y'all remember this? Where'd you get this, by the way? In circuits or in microelectronics? Circuits?
Analog.
Pardon?
Analog.
Yeah, who'd you have for analog?
Wentworth.
All right, if he did amplifier design, then he did something like this if he was doing complete amplifier design. But that's real important to be aware of, because engineers in general, I have found out, that come from I'd say people that take engineering like online and stuff like this, they get most of this, they never hear about the practical applications of life. That's a standard way to take ripple out of any kind of full wave or half wave rectification is with a pi filter. So I'm just showing you this. By the way, what kind of filter is that? If you were asked this on the spot, low pass, high pass, band stop. Just take one roll. Does it pass high frequencies, class? None, right? It's DC out, only DC. All the high frequencies get clobbered, and the cut frequency on this is at like 10 hertz. That's where the thing starts dropping off at 30 dB or 60 dB per decade. And I'm just telling you, this pi filter is used all the time. P filter is used, but usually for high frequency, high pass networks, more so than low pass. And here's why. Because you could have only one capacitor here. When you have 2, input output, this also will have a bleed rate that has to do with the impedance that you're feeding into right there. And it's much more helpful to have the capacitor right here than right here. I'm just telling you that right now, because this is experience. Is there anything you can think of a downside of this filter? This is sort of a hand wave kind of talk right now, but it's important to at least appreciate. What's one problem when you see L's and C's anywhere near each other in a circuit? There's one very important concept that should bring true. Resonance, right? So there's there's 2 frequencies where this thing goes into resonance. And when it goes into resonance, things get crazy, and here's why. Because then the voltages on this and this right here are the same magnitude, exactly 180 degree phase, and if you're pulling a lot of current, they can break down the voltage, right? They can go right through there and short it out to ground. Y'all hear me on that? So just remind yourself of the traps at resonance. Remind yourself, pi filter, real good for low frequency filtering. This is real good for high frequency filtering, right here. And here, you would have 2 caps in series, and you'd have an inductor shorted for high frequency. I'll leave it at that. Back to S parameters for this one. Let's do it over here. And you all see how either one of those 2, I could replace that resistor right there, and they could be used for the S parameters, right? It's a little more work to do with that, just want you to know. If they're all resistors, it's not bad, and as a matter of fact, we had a problem that looked just like this, only with resistors. I don't know if you recall that. Does anybody? we have 3 resistors? No. If you don't, it's okay. I want to go through the one with just 1 resistor for now. So let's go through the S parameters. Does anybody remember what S11 was? It was what? It's V1 minus over V1 plus, assuming what? V2 plus is 0. So this is the reflection coefficient of port 1. Is it a class? Everybody remember that? The symbol for reflection coefficient is capital gamma, like so. So how do we get that for this network? You'll notice I've shown you what? Generic values of Z naught, generic values of R, right? How do you do that? How do you get the reflection coefficient? Do you remember how I told you to do it? We need one thing right here for reflection coefficient. We need the input impedance right there, don't we? Y'all agree with that, class? What's the input impedance, Zn right there? On port 1. What's that?
R plus C naught.
Right. So that's R plus Z naught would be the input impedance, right? Now, how do you get reflection coefficient in general? You take the input impedance, right? Minus the impedance you came from, or the characteristic impedance of the line, over the input impedance plus the characteristic impedance of the line. Y'all agree with this? You with me on this, people? Y'all remember doing this thing? So what is it? Well, Zn right there is R plus Z naught minus Z naught over R plus Z naught or plus 2Z naught, or it's simply R over R plus 2Z naught, correct? That's it. You pick a value for R, value for Z naught, you got it for every possibility. So that would be S11. Now there's something you can get automatically by just observing the way that thing looks. Can we get S22, class? That's V2 minus over V2 plus, assuming V1 plus is 0, or the reflection coefficient of port 2. What is it and why, first of all? Y'all see it's a symmetric network? If I flip that around, if I look at it either way, it looks the same. Y'all agree with that? Everybody? Y'all know what I'm talking about? If I look at it this way, it has the same exact electrical characteristics as looking at it this way. Therefore, it is a symmetric network. Therefore, S11 is S22.
Does that only work when it's symmetric, or
Yes.
is it always symmetric?
No, it's not always symmetric.
Okay,
We'll
okay.
we'll do one that's not in 1 second. I'm trying to make sure everybody's up to date with this. Y'all, you guys got this, all right? Now, so that's gonna be the same thing, which is R over R plus 2Z naught. By the way, on final exams, I've never asked to fill out an S parameter matrix with arbitrary values. So don't fear that, but know how to do it, all right? Y'all understand what I'm saying? I'm not gonna give you too abstract a problem because people can get lost sometimes. So we've got S11 and S22 and S11. Now, how do we go ahead and get S21? Wayfair. Anyone? Well, what is it? Does anybody remember what the definition of that is? That's the forward amplification. Y'all remember that class? S21 is forward amplification. It's how much voltage we get out for how much we put in. So that's V2, right, minus over V1 plus, assuming what? V2 plus is 0. What it's really talking about a matched load in the second, matched load in port 2. In other words, 50 ohm load. Y'all follow me? So there's no reflections. Now, when we have that, what is this going to be? How do we get that? How many remember doing it? You don't, I'm not going to call on you. Y'all remember doing this? There was a key to this, right? We needed one thing. When we looked at port 1, if I had V1 plus right here, just before jump, right? Well, this, then right here, it's different, isn't it? we have to multiply it by the transmission coefficient to get that voltage just that hops off, you might say, the transmission line. So this voltage here, which I'll call V1 prime, is really the transmission coefficient at port 1 times V1 plus. I'm just trying to show you this to jog your memory. Y'all got that, class? How many remember seeing this? People? Okay. Now what do I do with that? Now I have the voltage there. What do I do next? No, we got the transmission coefficient. It's 1 plus the reflection coefficient. Don't worry about that. Suppose I got the voltage here and I want the voltage here. How do I get it? Voltage division. Do y'all follow me on this? Let me just draw it up here because I'm seeing a lot of stares that tell me maybe it's not so clear. So let me put it up here. We got S11 and S22. So if I look at port 1, right? And now here's that resistor, R. This is Z0. Over here, all that is matched, so this can look like just 50 ohms or Z0. Right? Y'all follow me? That's that transmission line over there is just Z0. Y'all follow me? Remember doing this? So if I want this voltage right here, which is V2, and it would be V2 minus, I take what? This is V1 plus coming at it, right? This voltage is going to be the transmission coefficient of port 1 times V1 plus, right? Do y'all agree with that? That's the voltage just inside here, and then I do simple voltage division. So to get V2 minus, I take the voltage transmission coefficient of port 1 times V1 plus, right? Then it's going to be times voltage division, which is Z0 over Z0 plus R. Y'all agree with that? Y'all follow me? Simple voltage division. And that gives me what? S21 is equal to V2 minus over V1 plus, assuming no reflection, it was matched, so it can't be. And you can see that that is the transmission coefficient on port 1 times simply Z0 over Z0 plus R. And here's something that you should see, it's real apparent. Hey, that's voltage division. This is just the transmission coefficient. And this rings true for every problem we do. The only thing you care about with any kind of either S12 or S21 is you want the transmission coefficient of the port you're looking at, and then the voltage divider, or the voltage division that occurs from there on. Y'all hear me on that, class? And it is that simple always. So this would be what? Well, my transmission coefficient is 1 plus my reflection coefficient, and that is the reflection coefficient, isn't it, class? I think, right? Isn't this the reflection coefficient of port 1? So therefore, this is going to be equal to 1 plus that, R over R plus Z0, right? Or 2Z0, pardon me. R plus 2Z0. And then it's times Z0 over Z0 plus R. And that's it. Now you can fuss with these values, but you can see that that transmission coefficient pretty much can go, if Z0 becomes very large, right, very large, let's make it infinity, then this term is 1. Y'all follow me on that? Take a look. And this term is 1 as well, so it can be 1. It can be an output to input of 1. Y'all follow me? That would be if Z0's going to infinity or R is going to 0. And it should make sense. What happens when R shorts out? Isn't it just a direct link from input to output? So it should be that. On the other hand, when R goes to infinity, then that forward voltage gain goes to 0, if you look at that. Got me on that, class? Last thing. If that's S21, what's S12? Isn't it the same? That's the reverse voltage gain. That's the voltage that comes out port 1 if a voltage comes in port 2. And they are not the same all, in general, they're not the same. For amplifiers, the reverse voltage gain is very, very small. Orders in order to, if it's designed right, orders in orders of magnitude less than the forward voltage. Got me on this, guys? We'll do one more because it's been a while. Now, I assigned problems, I'm certain on this. Do y'all remember the problems that I assigned, whether you did them or not?
You didn't post it on the window.
Did they not post?
No, sir.
What would they have been under? I'm checking.
It would have been 28, right?
I just went back and checked.
I thank you very much.
Thank
I
you.
will make sure today, I feel bad about this, but I thought for sure on Friday.
Yeah,
I was
they're.
looking forward to it on Thanksgiving.
That's what you're looking at
I
at
don't
dinner?
think There's sincerity. There's just not, I try not to give homework, but as you recall, I think I introduced you to S parameters.
Yes.
And I
Yeah.
just, I'm sorry if they didn't post, I wasn't gonna hold you accountable, I was gonna do this anyway, but I wanna make sure we're clear about it. Now, since they didn't post, they didn't post. Did somebody take them down? Anyway, let me go ahead and do another problem where it's not symmetric and make sure we all know this. That way I'll feel comfortable at least that I've covered the bases with this before I move into 3/4. Anything exciting this week?
Men's basketball,
Bruce Pearl gonna take his shirt off again?
hopefully.
What do we rank about? In basketball?
It's high teens.
We're in the top 20?
Mm-hmm.
Number 21st.
21st, I'm wrong. We must have dropped after that UConn
They
game.
were undefeated in that tournament, weren't they?
No, we lost it in double overtime against UConn.
Didn't we really?
Yeah, it was an exhilarating game. Like you couldn't be mad after watching it, just how good it was, because we came back by 15 points. Huh?
My wife could be, she was furious about the Iron.
Oh well, you could be mad about that one.
You don't know what happened. I have to live in it now. All right, here we go. This is non-symmetric with real numbers. See, this is the kind of problem you'll see on the final. All of a sudden, final.
All of a sudden, everybody
What
got
were you
quiet.
saying there? And maybe even the quiz. All right. I'm gonna take a 50 ohm line here. Now, this is gonna be a little tricky, so listen carefully. This is gonna be Z naught on this side is 50 ohms, all right? Here, I'm gonna come in, I'm not gonna put any inductors and capacitors, just make things a little simpler. Now I'm gonna take, and I'm gonna put a resistance here of 50 ohms. And then I'm gonna put a resistance here of 200 ohms. All right. Then over here, I'm gonna go ahead and put Z naught here. This would be the second one, Z naught equal to 200 ohms.
Okay.
This is port 1. This is port 2. By the way, this would be a rarity where you would have two different impedances, one coming in and one coming out. But it does happen with when you're dealing with radar. This will happen on it at times. So you're going to have a device like that, 50 ohms in series, 200 ohms in parallel with port 2. And you want to figure out the S parameters, okay? Now, just work with me on this one. We're going to go through it. It's not symmetric. We all agree on that. Anything but symmetric. And it's odd because now Z naught's not even the same on both sides.
Mm-hmm.
So we start by getting S11, which is V1 minus over V1 plus, assuming V2 minus, or V2 plus is 0. And that's still the reflection coefficient of port 1, right? So what's the key to getting the reflection coefficient of port 1, anyone? That's right, the input impedance to port 1. So if we look here, what is the input impedance right here? Just take a look and tell me. There's no wrong answers. What do you see if looking through here? You got 50 in series for sure, right? What next?
200's in parallel.
You see 200 in parallel with 200 or 100 ohms, correct, class? So you can see pretty clearly that that's gonna be what, 150 ohms, isn't it? 50 in series, 100 there, so it's 150 ohms. I just put it ZN1 is 150 ohms. All right, so what's the reflection coefficient of port 1? Impedance you're going into, right? Right, in port 1, which is going to be 150 minus the impedance you came from, 450, right? Over the sum of the two, or over 200. So that's going to be 100 over 200, or 1/2. Y'all agree with that? All right, let's keep going on this. Just see if you can get these things. I'm going to go through them sequentially. I got that. Now I want S21. I'm still on port 1. Well, S21 technically is V2 minus over V1 plus, assuming V2 plus is 0. So it's really the forward voltage gain, right? Y'all agree? All right, how do we get that? You remember the key. There's just two things you always have to do. One is the transmission coefficient of port 1 you need, don't you, class? We have to find how much of the voltage coming in right here at port 1, V1 plus, that's coming in, develops here, right? And so this voltage will be the transmission coefficient of port 1 times V1 plus. Please try to make sure that's seared in your mind. Y'all with me? All right, what is the transmission coefficient of port 1? Class?
Plus reflection.
1 plus reflection coefficient of port 1.
So 1.5.
3/2, exactly. It's greater than 1. This is like, how can that be? It can be. It just means the reflected wave is negative. It can be. Don't worry, it can be. Y'all with me? Now what? Well, I got the voltage here, then what do I do?
Voltage division.
Voltage division, y'all agree with that? So now, for this one, I'm gonna not even bother with the V1 plus term. I know that's gonna cancel out. So it's gonna be a transmission coefficient, where it's gonna be 1/2. And then for voltage division, what is it? Doesn't this circuit really look like plus or minus right here, coming in 50, right? And then this looks like just 100 ohms, right? And this is the voltage I want. Isn't that right, class? So what's the voltage division gonna be? It's hard to say.
100 over 150?
It's the incoming voltage here times 100 over 150. Y'all see that, class? Just making absolutely sure. So it'd be 100 over 150, right? And there, what do I get?
One.
Well, that's gonna be 1/2 times what?
One half or is that
It's 3/2.
It's supposed to be 3/2.
Oh, I'm sorry, 3, my bad. 3/2, my bad. 3/2 right here, right? Over 2, isn't that right, class?
Yep.
What do you notice?
It's just one.
1. That should bother you, but don't worry. Power is always conserved. Even though the voltage is gonna go up there, the power, it's gonna be the same, the power will be conserved. Y'all agree with this, class, what we just did? How many see this? All right, we're not done. Now, what about S22? That's what? The reflection coefficient on port 2, isn't it, class? So what's that gonna be?
Zn on the port 2 and Z naught. So would it
That's right. So it's going to be Zn. Well, let's first find out what Zn on port 2 is. Pay attention to this one. This is 2. Now, I want you to hear me here, because here's where mistakes are made. When you're doing the input impedance, you don't include that. You come right here and you look this way. Y'all hear me? So when I'm looking there, do you see I have 200 ohms? In parallel with 50 and 50, or 100 ohms, don't I? Can you all see that? Look here. If I'm looking from here over, I've got 200 ohms of drive, Then I have 50 there. And then here to ground, I have another 50, right? Are you with me? Do y'all see it? So what's the input impedance right here, if I'm looking this way? Don't these look like 100? Right? It's 100 in parallel with 200, right? So what is that?
Simply 150.
Right, it's 60, it's really 2/3 of 100, isn't it? So this is gonna be, the input impedance here is gonna be 2/3 of 100. I'm gonna leave it just like that. Y'all with me? That's 66. Okay? Now, once I have that, what's that gonna be? Reflection coefficient at port 2. Think about it now. That's the impedance I'm going into, right? Which is 2/3 of times 100. Do y'all agree that's the impedance I'm going into? Minus the impedance I came from, minus 200, right? Over what?
Those two added.
That's right, which is gonna be what? 2/3 times 100 over plus 200. I don't know what that is, but I know it's negative. Let's see, we've got 2/3 minus 2 over 2/3 plus 2, so that's gonna be 6 and 2.
Yeah, minus 1/2.
Is it minus 1/2?
Yeah.
Y'all agree with that, class?
Oh, yeah, sure.
All right, now, so that's the reflection coefficient there. So this is S22, right? And that means the transmission coefficient at port 2 is going to be 1 minus 1/2, or it's going to be 1/2. Y'all agree with that, class? 1 plus reflection is transmission at port 2. Agreed? All right, now let's get S12. That's the reverse voltage gain. So what is S12 going to be, class? This is the kind of problem I will put on a final exam. I'm going through it in detail to show you the thought process, to make sure there's not something, because here's what happens in a lot of this. You get very comfortable and casual, always knowing these two impedances are the same. Y'all with me? So when they're not, all of a sudden, you kind of just think they are, and you make these gross mistakes. Don't do that. Y'all with me, class? The way I'm going through the reasoning on this one, make sure you do. So what is S12? It's V1 minus over V2 plus, right? Assuming what? V1 plus is 0. So that's the reverse voltage gain. How do we get that? Just like we got the forward voltage gain, except what? I'm starting at port 2 here, and now I'm going to have my V2 plus coming in, right? Please watch this. You agree with me? And it's the same process. Now I need the voltage just on the inside of this filter right here. I need this voltage just after it jumps off where Z0 is. So this voltage, V, call it V2 prime, that would be the transmission coefficient at port 2, port 2 times V2 plus, right? Y'all with me? It's just like we did before when we reversed it. That's the voltage there. Then what do I need to do with that voltage? To get the output voltage here?
Voltage division.
Voltage division. And here it's important you see this. So I'll draw it here. I've got 200 ohms, like so. This is where Z02 is. Then I have 100, or I'm sorry, I have 50, right? And then I have the transmission line, which is also 50. And I want this voltage. So, you all see that this one doesn't do a thing. You all see that. The only thing that matters is this voltage division, which is what? 50 over 50 plus 50, or 1/2. Y'all follow me on that? So that means S12 is going to be the transmission coefficient at 2, which is 1/2. We just put that down there. And then it's gonna be times the voltage division, which is 1/2 as well, correct, class? And you can see that's 1/4. And that, in fact, is how you get the S parameters for that system, which is a little, I'm struggling for a word. It's different than anything you've seen because there's not, the Z naught is different in both cases. That's the big deal. And it's also not symmetric. But here's the next stage of this, and this, you get problems on this tonight. Now, so far, everything's been strict real, right? If you wanted to have a lossless S parameter system, hear me now, something that had no power loss, then what they would do is this. There would be no resistors, there would be inductors and capacitors. Anytime you have just a filter network with inductors and capacitors, there is no power loss, remember that. And that's real important because you don't like power losses. We're gonna get to splitters in a second. So that's basic 2 ports, and I did an asymmetric one that had uneven or unequal Z naughts on either side. And I did a symmetric one for starters. Now we're gonna do 3-port, okay? And this is, you can almost imagine, this could go to N port, but it's really a relation of input to output. Can anybody, I mentioned this before, but can you give me an example of a 3-port device that you encountered? I'm sure a lot of you have actually messed with it and installed it. And it has to do with cables. You know what a splitter is?
Mm-hmm.
How many have done something with a splitter that comes into your house or apartment or anything, where you've taken one line and made it into 2, right?
Yep.
That'll work great. It'll work great for about 2 splits maybe if you got a strong signal. But then all of a sudden you lose signal and you can't do crap with it. And that's how come you need these amplifiers to amplify the signal too. But those splitters are resistor splitters. They're simple. They're 3-port devices, but they're simple splitters that lose power. And we're going to go through that. So now, with 3-port devices, you can draw them any way you want. Basically, it's like this. A lot of times they're called circulators. This will be port 1. And you've got something coming in there, the V1 plus. Actually, they're not always called circulators. That's not a fair statement. This would be port 2. And this would be port 3. They can be numbered any way you want. This is something that has S parameters. And the way S parameters always work is you take, we're assuming V1 plus comes in, V1 minus goes out. V2 plus comes into port 2, and V2 plus comes out. Or, I'm sorry, V2 minus comes out. Here, V3 plus comes into this port, and V3 minus goes out. Then we write the equations just like we did prior, but we add one more term. So we start with V1 minus is now equal to S11 times V1 plus. That's the reflection coefficient. Then it's S12 times V2 plus. That's the reverse voltage gain from port 2. Then you add on S13 V3 plus, and that's the voltage, reverse voltage gain from port 3. Y'all hear me on this, class? So we're adding that extra term. V2 minus is again going to be equal to S21, so this is going to be the forward voltage gain, V1 plus S22 V2 plus, that's the reflection coefficient at port 2, plus then it's going to be S23 V3 plus, and that's the voltage gain from port 3 to port 2. Forward voltage, or I guess it's a reverse voltage. Y'all follow me on this? It's just standard way of doing it. Finally, V3 minus, right there, is going to be S31 V1 plus, And again, it's a voltage gain, but it's going what? In the wrong direction, right? Well, actually, this is the right direction. It's coming out of V3 minus. Then it's going to be plus S32 V2 plus, and this is the reflection coefficient in port 3, V3 plus, and that's the equation, and in general, it's written as that block, like this. We have S11, S22, S33, S21, S31, S32, S23, S12, S13, times V1 plus, V2 plus, V3 plus. And that's a 3-port designation for the voltage gains and reflection coefficients. Now this happens a lot. And here's the one thing I want to tell you. We'll get to splitters in 1 second, but a lot of times you have what are called circulators. Has anybody heard that? Circulator before? That term? In radar we use it in a lot of different things. And here's what happens. What they'll say for a circulator, and I'm going to show you, they want all of the signal incoming to port 1 to come out port 2. They don't want any of the signal going to port 3. So everything coming in port 1 goes out port 2. Then they want everything coming in port 2 to come out port 3. Can anybody think of an application for that? Well, with a radar system, you'll have one transmit and receive antenna. You'll have a power amplifier over here that you'll toggle the power on. And all that power you want fed to the antenna. And then it goes dead and listens. But you want to make sure all the receive signal comes out a different port for analysis. You'll take that, you'll amplify it a little bit, and you'll take it, then go from an A to a D, and then you do digital signal processing. But this is why it's important with radar. And it's important in any two-way communication system that uses the same antenna for both. It is. Then they'll have all of port 3. You don't have to have this part, but it's usually the way it's done. Come out port 1. And port 3 will never have anything coming in that way if it's a radar thing. So now how would you get those parameters? I'm asking you this, and I know I'm about out of time. Think about it logically. There's the matrix, right? So if we had a circulator, and we fed the S parameters. Now just think of the things you know. The voltage gain from here to here has to be 1, doesn't it? That would be 1. S21, right? Whatever comes, the 2-1 is the forward voltage gain, has to be 1. Where's S21 right here? So here's the first entry. This would be 1. Right? Now what else? We want the voltage gain into port 2, out of port 3. So it'd be S32, wouldn't it, class? 3, S3 is the ports coming out of 2 is the ports coming in. So where's S23? That's here, isn't it?
It's 3-2.
Or I'm sorry, S32, it's down here, right? It's 1. Where else do we want 1?
3.
We want S13, right? Where's 13 right there? Y'all see that? You understand the reasoning behind it, right? These are just voltage gains from one port to another. You have to identify the S parameter that controls that. All the rest you would like to be 0. You would like no reflection coefficient. These are all zeros ideally, because you want no coupling from this port in the reverse direction of this port or any such. Y'all follow me? So once you have that'll be an ideal circular. It's in your book. I want to just mention one thing. It's never ideal. Never. These might be low. I mean, this reflection coefficient here, it might be like 0.01, 0.001. It's still going to be something measurable and something you have to do with. So usually what they do when they display S parameters for things like this, they'll take the log of that. They'll take 20 times the log of these things, and it'll be S parameters in DB. Y'all understand that, class? So now I'm gonna give you some homework with this stuff. We'll finish up 4-port, and I'll go through some more stuff on Wednesday. Thank you for being here. Thank you for recording. And I'll get this back to you. Your stuff as soon